Hi, we start today our exploration of methods of numerical integration. Here's an outline. In this short video, we will simply give a motivation and introduce the general concept of a numerical quadrature, and we'll leave for future videos discussing the different types of quadratures, Newton-Cotes quadratures, Gauss quadratures, and composite rules. Now, motivation. Our goal is to compute definite integrals, that is, the integral of some function f in interval a, b. In some cases, we can resort to analytical integration, but we are aware of the limitations of this approach in some applications. For instance, the analytical expression of f may be unknown, as we illustrated in the first exercise. Maybe f is a black box, so we can evaluate f for a given point, but not see its analytical expression. Maybe f is only available at some given points xi, so f is given in a discrete manner with no analytical expression. And maybe even if f has a known analytical expression, maybe it's difficult or simply impossible to obtain a primitive. In all these cases, we can use a numerical quadrature. The idea is the following. We will approximate the integral by means of a sum of function f evaluated at some points xi with weights wi. So, for instance, in this figure, we have interval a, b, and we have chosen integration points x0, x1, down to xn. And the goal is to approximate the integral as a weighted sum of images f x0, f x1, dots f xn. If we approximate the integral by means of the sum, the integration or truncation error is en. Now, once we have selected the integration points, how can we obtain the weights and the expression of the error? We will use this general approach. It is very simple and yet powerful. Two phases. We will first approximate f by a polynomial, and then we will take the integral of the polynomial as an approximation to the integral of function f. In some more detail, we will approximate f by a polynomial of degree n using Lagrange interpolation with integration points xi. As we already know, because we choose Lagrange polynomials as our polynomial basis, the images of f at the integration points play the role of coefficients of linear combination. Rn is the interpolation error, the Lagrange remainder. We then simply integrate this expression here to obtain that the integration weights are simply the integral of the Lagrange polynomials, and the truncation or integration error is simply the integral of the Lagrange remainder. Please note how we took scalars f xi outside the interval. A graphical illustration. Imagine we are working with n equal 2, that is, with a quadrature with 3 integration points, x0, x1, and x2. That is, we sample function f to obtain f(x0), f(x1), and f(x2). Then, by means of Lagrange polynomials, we obtain the only polynomial of degree 2, the only parabola that passes through these 3 points, something like this. So this is p2x. And now we take the area below the blue line as an approximation to the area below the red line. And please note that although P2 is a poor approximation to F, the areas may be quite similar because there can be compensation between this negative area here and this positive area here. How can we classify numerical quadratures? How can we classify formulas of numerical integration? We'll discuss 2 classifications. First one, depending on the integration points. 2 types, Newton codes and Gauss. Now, in Newton codes quadratures, integration points are arbitrary, given, imposed by the problem. In many applications, but not in all applications, they are equispaced integration points. And we then only have to determine weights and integration error EN. Whereas in Gauss quadratures, integration points are optimal in a sense to be discussed and are thus associated to the quadrature. Like before, we also need to determine weights and integration error. How do we choose between Newton codes or Gauss quadratures? Well, if f is only available at some discrete points, for instance because f are experimental measures, well, these discrete points will have to be the integration points, so we're thinking of a Newton codes quadratures. Whereas if f can be evaluated anywhere in interval AB, then we can work with optimal integration points. We are thinking of a Gauss quadrature. Second classification, we called a quadrature closed or open, depending on whether the endpoints A and B are taken as integration points or not. Please note how in an open quadrature A and B are not used as integration points. To finish, we'll discuss the notion of order of a quadrature. We say that the quadrature is of order Q if it integrates exactly all polynomials of degree less than or equal to Q. In other words, we are using polynomials as reference functions to judge the accuracy of a quadrature. How can we determine the order of a quadrature? Discuss 2 ideas. First, if the quadrature is obtained by integrating the interpolating polynomial Pn using n plus 1 points, then it is a simple exercise to show that it has order n or higher. Second idea, if we can establish that the integration error of a quadrature can be expressed as some constant times the derivative of order q plus 1 at some intermediate point mu in interval ab, then we are sure that the quadrature has order q, simply because a polynomial of degree q has derivative of order q plus 1 identically equal to 0.